This topic was chosen by one of our patrons. Hello mortals. Ever heard of quantum physics? I'm sure you did. Biology? Of course. Now what about
quantum biology?
This is not a simple combination of words to make you sound intelligent, but an entire field of study which analyzes the applications of quantum mechanics to biological objects in order to explain things like random mutations in DNA, how do birds orient themselves while migrating, how does photosynthesis work, and even what's going on in the US politics. One of them is a lie. After watching some top anime crossovers, the first person to think of combining quantum mechanics and biology was none other than our cat-loving Erwin Schrödinger. He even wrote an entire book on this topic. There, he introduced the idea of an aperiodic crystal which contains genetic information in its chemical bonds. Afterwards, he suggested that mutations in this crystal somehow happen because of quantum leaps, electrons jumping from one energy level to another. After a few years, a molecular structure in cells which preserves information was discovered, now known as DNA, which acts as the instruction for making proteins. It consists of these 5 nucleotides. Inside the DNA, those nucleotides are tied in pairs by several hydrogen atoms and form this well-known spiral. We will focus on only 2 of those pairs. During the DNA replication, there is a small chance that the hydrogen atoms will change their places, thereby transforming the GC pair into the TA pair, or vice versa. This will cause an alteration in the genetic code and therefore, a mutation. However, this transfer of a hydrogen atom from one place to another requires a lot of energy and cannot be explained by well-known mutation models such as ultraviolet radiation, oxidative damage, or this thing. Then the Swedish physicist Per-Olof Lodin came and presented his quantum model of mutations in biochemistry. He suggested that this transition is made possible due to
quantum tunneling.
Bet you didn't see that one coming, huh?
This weird thing is a phenomenon where a subatomic particle passes through a potential barrier that it cannot surmount under the provision of classical mechanics. In other words, it permits the teleportation of a particle to a place where it shouldn't be able to get because of the lack of energy. For example, by quantum tunneling, the hydrogen particles are able to form helium nuclei. That's how the fusion process works inside the Sun. If we look at the Schrödinger equation which describes this process, we'll see that the probability of tunneling depends on the mass of the particle. In other words, the heavier the particle is, the less of a chance it has to tunnel. And this fact was used to demonstrate the Lodin theory. Now what if we replace the normal hydrogen atom from the DNA, with its heavier isotope, deuterium? In this case, quantum tunneling should occur less often and thereby the rate of spontaneous mutations will decrease. And recent experiments prove that. Scientists grew a culture of bacteria in a deuterium oxide environment, and their cells showed fewer mutations than bacteria grown in normal water, proving Lodin's theory. So you can thank quantum physics if you have a lactose tolerance or no wisdom teeth. Now moving on to photosynthesis, the process of converting solar to chemical energy in plants. They absorb the energy coming from the sun in form of photons using the chloroplasts inside their cells, which contain some special molecules called chlorophylls, the ones that give leaves their green color. So, when the photon gets inside a chloroplast's antenna and hits a chlorophyll, one of its electrons gets excited and uses the extra energy to bounce through the antenna from a molecule to another to a reaction center. There, the gathered electrons create a permanently separated charge that is, in essence, stored energy ready for use by the plant. There is a problem, however. Getting to the reaction center is a very hard procedure to accomplish, because in one chloroplast's antenna there are hundreds of thousands of chlorophylls. And this intermediary action of passing from one molecule to another has to be done quickly. If the electron doesn't get there in a nanosecond, bouncing randomly through the molecules will absorb all of the photon's energy, making the whole process useless. So the electron has to find the shortest path from the first molecule to the reaction center. But how? The plant doesn't know of any pathfinding algorithm to get the shortest trajectory for every electron. Here's where quantum physics comes into play, and more precisely,
quantum superposition.
This principle states that a particle can be in various places at the same time, thus occupying multiple positions at once. And it turns out that plants and algae employ quantum superposition so that the electron can simultaneously travel among all possible paths. That way, it always gets to the reaction center every time through the shortest path. But do you know what can be cooler than eating light? Being able to smell magnets. That's exactly what magnetoreception is. The ability of feeling the magnetic field's lines, direction and intensity, knowing where the poles and the equator is used by a range of animals for navigation and migration. As an example, we'll take the migratory birds named European robins. Those feather balls migrate each year from northern to southern Europe and vice versa using the Earth's magnetic field. But how exactly do they detect it? Well, scientists don't know the exact answer, though there are some hypotheses. The most boring one is that they have a substance named magnetite somewhere in their body which is sensitive to the magnetic field. However, the most fascinating theory is as always the one that has quantum physics in it. It says that migratory animals use a special protein in their eyes named cryptochrome. When a photon enters the eye and hits one of those molecules, one of its electrons bounces away and gets to another cryptochrome, forming that way two radicals, one negatively charged and one positively. And here's where we introduce
quantum entanglement.
I spoke about this principle in this video and you can go and watch it to understand what it is, but briefly, quantum entanglement is the ability of two electrons from the same energy level to keep opposite spins. And even after one of the two entangled electrons leaves the energy field, both electrons will keep opposite spins relative to each other. Same with the electrons of the cryptochromes. Depending on the electron's spin, it reacts differently to the magnetic lines, and in that way, it allows the pair of radicals to align themselves to the magnetic lines and react differently at different angles. In that way, those animals can understand where they are located in reference to a magnetic pole on the equator. And these hypotheses aren't the only ones that use quantum physics at explaining biological phenomena. Others, like the sense of olfaction, vision, the effectiveness of enzymes and even the presence of consciousness could also be explained using principles from quantum mechanics. And maybe this way, you insignificant mortals, will feel as being part of the quantum world, part of something bigger, something important, at least for a little bit. Not that it would change anything.
Many of our viewers have asked us a very serious question. What if we made a big pile of bombs and exploded every nuclear weapon in the world all at once? Strangely enough, we couldn't find a good source to answer this question to our satisfaction. So, we gathered together a few scientists to calculate what would happen and find an answer to this extremely important scientific problem once and for all. Currently, there are 15,000 nuclear weapons on Earth. The US and Russia both have around 7,000, while France, China, the UK, Pakistan, India, Israel and North Korea own around 1,000 between them. But how much destructive power is this really? Let's try to put these numbers into perspective. On Earth, there are about 4,500 cities or urban areas with at least 100,000 inhabitants. Some are bigger than others, so we'll assume that on average we need 3 nuclear bombs to completely wipe out one city. This means we could destroy every single city on planet Earth with our nuclear arsenal, killing more than 3 billion people, roughly half of humanity, in an instant. And we'd still have 1,500 nuclear weapons left. Now that's what an expert would call overkill. So we can say with confidence that we have a lot of nuclear weapons and they can do a lot of damage. But what if we make a huge pile of all 15,000 bombs and pull the trigger? Let's drop our nuclear pile in the middle of the Amazon rainforest, just to show nature who's boss. Our warheads, piled haphazardly, fit into a small warehouse. A typical US warhead has the power of 200,000 tons of TNT. So 15,000 warheads would be the equivalent of 3 billion tons of TNT. For scale, this is enough to rebuild the whole island of Manhattan with every building and skyscraper using stacks of TNT. The closest thing we can compare to the energy gathered here is a volcano. One of the deadliest volcanic eruptions in recorded history took place in 1883 on the island of Krakatoa. The eruption was so powerful that 70% of the island and the surrounding archipelago was destroyed, killing tens of thousands of people. Its effects were felt around the world for days after the event. Our nuclear pile contains 15 times the energy of the Krakatoa volcanic eruption. So let's finally push the button. 3, 2, 1. In a second, a fireball 50 kilometers across vaporizes everything in its way and creates a blast wave that flattens 3,000 square kilometers of forest. Every living thing within 250 kilometers will start to burn. The explosion will be heard literally around the world as the pressure wave circles the Earth tens of times over the next few weeks. Millions of tons of incinerated material are catapulted into the atmosphere. The mushroom cloud reaches the outer reaches of the stratosphere, pushing up against space itself. After things have calmed down, a small crater, about 10 kilometers across, is left in the center of the worst wildfires the planet has seen in millennia, spreading throughout South America, burning down forests and cities alike. And now, the unpleasant part begins. Extremely radioactive material will kill living things very quickly, and a large area several kilometers around the crater is now uninhabitable, as is everywhere for hundreds of kilometers downwind. Much of the fallout is carried high into the atmosphere by the mushroom cloud and carried around the planet. The amount of radioactive material in the environment doubles worldwide, which still isn't civilization ending, but we may see more cancer for a while. A portion of the particles will float at the edge of space for years and cause a nuclear winter that could lower global temperatures by a few degrees for a few years. This explosion was pretty bad if you're in South America and especially Brazil. The Amazon rainforest is pretty much history, which is not great, but human life will go on. Okay, but what if we explode more nuclear weapons? Let's suppose humanity decided to mine every bit of uranium on Earth and build as many nuclear bombs as possible. At current usage, it's estimated that there are around 35 million tons of uranium in Earth's crust, enough to power human civilization for over 2,000 years, or to build millions of nuclear warheads. For the sake of argument, let's say we create a pile with the yield of 10 billion Hiroshima bombs, which makes up a cube 3 kilometers high that contains roughly the energy of the asteroid impact that ended the age of the dinosaurs 65 million years ago. Except it's also nuclear. 3, 2, 1. Our pile explodes in a fireball stretching so high into the sky that it's visible from half of South America, with so much power that the ground just splashes like water, forming a crater 100 kilometers across. Bedrock on the scale of whole mountain ranges is vaporized in an instant, while thousands of tons of material is catapulted away with such speed that it's ejected into space. Some leaves Earth forever, while most of it comes raining down as hot, burning debris that heats up the atmosphere to oven-like temperatures, killing most big animals and causing firestorms all over the world. The Earth's crust rings like a bell, struck by global earthquakes stronger than anything in recorded history, decimating cities around the world, while hurricane-force winds flatten every single tree in South America and wildfires consume the continent. The abundance of hydrocarbons in the Amazon burned to form ash are cast into the atmosphere, darting the sky and keeping sunlight from reaching the surface, dropping temperatures to near freezing worldwide. The ensuing global winter may last for decades and results in the extinction of every large animal species, humans included. We could also mention that every corner of the planet is covered with radioactive fallout, but at this point, it doesn't matter that much anymore. This is humanity's extinction event. The astronauts aboard the International Space Station get to enjoy a great view for a while, but it's not unlikely that the spray of rocks blast into orbit will destroy the station. Those lucky enough to be in bunkers or in submarines deep below the ocean surface may survive the longest before they exhaust their food supplies and have to venture out for more. They'll find the world a charred, freezing, radioactive wasteland. The planet itself doesn't care at all. After just a few million years, the wounds of the explosions have healed and life is thriving, arguably even more so than when humans were around. If intelligent life emerges again, it might be able to work out what happened. When they study geology, they'll find a bizarre and very thin layer of rock covering the entire world, enriched in radioactive elements like uranium and the other nasty things it decays to, mixed with rare earth metals and plastics that humans used. They would probably be very, very confused. Videos like this one take well over 1,200 hours to finish. Over the years, we put more and more effort into research, conversations with experts, illustration and animation, sound design and fact-checking. For this video, we put a lot of extra work into our sources document. You can read how we got to the information in the video, what our experts thought about it, where they disagreed with each other. We can take the time to do this because of you, our viewers. Because you watch and share our videos, buy our posters and support us on patreon.com. If you like what we're doing, please consider becoming a patron or get one of the nice things we made with love. Thank you for watching.
And now, ASAP Science presents the elements of the periodic table.
There's hydrogen and helium, then lithium, beryllium, boron, carbon everywhere, nitrogen all through the air with oxygen so you can breathe, and fluorine for your pretty teeth, neon to light up the sign, sodium for salty times,
Magnesium,
aluminium, silicon,
phosphorus,
then sulfur, chlorine, and argon,
potassium,
and calcium so you'll grow strong,
scandium,
titanium, vanadium, and chromium, and manganese. This is the periodic table, noble gas is stable, halogens and alkali react aggressively. Each period will see new outer shells while electrons are added, moving to the right. Iron is the 26th, then cobalt, nickel coins you get, copper, zinc, and gallium, germanium, and arsenic, selenium, and bromine film, while krypton helps light up your room, rubidium, and strontium, then yttrium, zirconium,
niobium,
molybdenum, technetium,
ruthenium,
rhodium, palladium,
silverware,
then cadmium and indium,
tin cans,
antimony, then tellurium, and iodine, and xenon, and then cesium, and barium is 56, and this is where the table splits, where lanthanides have just begun, lanthanum, cerium, and praseodymium. Neodymium's next to promethium, then 62, samarium, europium, gadolinium, and terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium, hafnium, tantalum, tungsten, then we're on to rhenium, osmium, and iridium, platinum, gold to make you rich till you grow old, mercury to tell you when it's really cold, thallium, and lead, the bismuth for your tummy,
polonium,
astatine would not be yummy,
radar,
francium will last a little time,
radium,
then actinides at 89. This is the periodic table, noble gas is stable, halogens and alkali react aggressively. Each period will see new outer shells while electrons are to the right. Actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, isonium, fermium, and olevium, nobelium, lawrencium, rutherfordium, wm, sprigium, boreum, hesium, pneumonium, dubsidium, rhenium, copernicium, nihonium, flerovium, moscovium, livermorium, tennessine, and oganesson, and then we're done. Thank you guys so much for watching. If you liked the song, make sure you check it out on iTunes and Bandcamp with the link below.
If you think you'd enjoy other videos like this, make sure you subscribe to our channel, and we'll put some of our recent videos over there so you can go check them out.
You can also check out asapscience.com to keep up with everything, what's the latest with ASAP Science, including stuff like new merch. Otherwise, we will see you next time. Peace.
The fundamental currency of our universe is energy. It lights our homes, grows our food, powers our computers. We can get it lots of ways: burning fossil fuels, splitting atoms, or sunlight striking photovoltaics. But there's a downside to everything. Fossil fuels are extremely toxic, nuclear waste is, well, nuclear waste, and there are not enough batteries to store sunlight for cloudy days yet. And yet, the sun seems to have virtually limitless free energy. Is there a way we could build a sun on Earth? Can we bottle a star? The sun shines because of nuclear fusion. In a nutshell, fusion is a thermonuclear process, meaning that the ingredients have to be incredibly hot, so hot that the atoms are stripped of their electrons, making a plasma where nuclei and electrons bounce around freely. Since nuclei are all positively charged, they repel each other. In order to overcome this repulsion, the particles have to be going very, very fast. In this context, very fast means very hot. Millions of degrees. Stars cheat to reach these temperatures. They are so massive that the pressure in their cores generates the heat to squeeze the nuclei together until they merge and fuse, creating heavier nuclei and releasing energy in the process. It is this energy release that scientists hope to harness in a new generation of power plant, the fusion reactor. On Earth, it's not feasible to use this brute force method to create fusion, so if we wanted to build a reactor that generates energy from fusion, we have to get clever. To date, scientists have invented two ways of making plasmas hot enough to fuse. The first type of reactor uses a magnetic field to squeeze a plasma in a donut-shaped chamber where the reactions take place. These magnetic confinement reactors, such as the ITER reactor in France, use superconducting electromagnets cooled with liquid helium to within a few degrees of absolute zero, meaning they host some of the biggest temperature gradients in the known universe. The second type, called inertial confinement, uses pulses from superpowered lasers to heat the surface of a pellet of fuel, imploding it, briefly making the fuel hot and dense enough to fuse. In fact, one of the most powerful lasers in the world is used for fusion experiments at the National Ignition Facility in the US. These experiments and others like them around the world are today just experiments. Scientists are still developing the technology. And although they can achieve fusion, right now it costs more energy to do the experiments than they produce in fusion. The technology has a long way to go before it's commercially viable. And maybe it never will be. It might just be impossible to make a viable fusion reactor on Earth. But if it gets there, it would be so efficient that a single glass of seawater could be used to produce as much energy as burning a barrel of oil with no waste to speak of. This is because fusion reactors would use hydrogen or helium as fuel, and seawater is loaded with hydrogen. But not just any hydrogen will do. Specific isotopes with extra neutrons, called deuterium and tritium, are needed to make the right reactions. Deuterium is stable and can be found in abundance in seawater, though tritium is a bit trickier. It's radioactive, and there may only be 20 kilograms of it in the world, mostly in nuclear warheads, which makes it incredibly expensive. So we may need another fusion buddy for deuterium instead of tritium. Helium-3, an isotope of helium, might be a great substitute. Unfortunately, it's also incredibly rare on Earth. But here, the Moon might have the answer. Over billions of years, the solar wind may have built up huge deposits of helium-3 on the Moon. Instead of making helium-3, we can mine it. If we could sift the lunar dust for helium, we'd have enough fuel to power the entire world for thousands of years. One more argument for establishing a moon base if you weren't convinced already. Okay, maybe you think building a mini sun still sounds kind of dangerous. But they'd actually be much safer than most other types of power plant. A fusion reactor is not like a nuclear plant, which can melt down catastrophically. If the confinement failed, then the plasma would expand and cool, and the reaction would stop. Put simply, it's not a bomb. The release of radioactive fuel like tritium could pose a threat to the environment. Tritium could bond with oxygen, making radioactive water, which could be dangerous as it seeps into the environment. Fortunately, there's no more than a few grams of tritium in use at a given time, so a leak would be quickly diluted. So we've just told you that there's nearly unlimited energy to be had at no expense to the environment in something as simple as water. So, what's the catch? Cost. We simply don't know if fusion power will ever be commercially viable. Even if they work, they might be too expensive to ever build. The main drawback is that it's unproven technology. It's a $10 billion gamble, and that money might be better spent on other clean energy that's already proven itself. Maybe we should cut our losses. Or maybe, when the payoff is unlimited clean energy for everyone, it might be worth the risk. Videos like this one take hundreds of hours to make and are made possible by your contributions on patreon.com. If you want to learn more about global energy, here's a playlist about nuclear energy, fracking and solar power. Let us know in the comments if there are other technologies you want us to explain.
Welcome to Science Wars,
Chemistry,
Bio, Physics,
Mathematical,
which field is best? I understand the force and energy, quantum mechanics and relativity. My field is pure and they rely on me. I see the universe like nobody. You may have made fun of me in high school for being awkward and following the rules. Now I've got lasers.
Wow, that's really cool.
May the mass times acceleration be with you. Atoms, entropy, dark matter, string theory.
If you want to feel a bond, then I can give you a good reaction. The elements that make up life are my essence and my satisfaction. All the other fields out there are so basic, yeah, I'm the central science. Keep your eye on me, I'll get you charged. If you need me, call me up on Avogadro's number. If you leave me, take a Titran, shove it up your acid buffer. Dopamine and serotonin will keep you good and happy. Just get your flask and your glass all set up and begin to understand the world.
Within me, you'll find life's beauty, from genetics to ecology, symbiosis and not division, unless it's mitosis or the study of fission. Even if you don't pass, you'll enjoy my class. Evolution has brought us along, all species, oh, singing one song.
If you want to learn about the world, I must say I am the purest field of study you can take. Immune to misinterpretation, the blueprint of creation, the backbone of all things science. No bias, just constant augmentation with your mind and observation. No gadgets, just your logic and your time.
And together we will find the answers to life with physics, biochemistry, and math. We can science.
Hello mortals, guess what happens when you divide something by 0? You are right, you get a black hole. And that's what we are going to speak about. Some of them are tens of billions of times more massive than the Sun, while others, smaller than atoms. Right now, You are being held on the surface of the Earth by its gravitational attraction, which is kept in orbit by the Sun, which, together with the whole solar system, orbits the galactic center of the Milky Way, which, in turn, is kept together by Sagittarius A, a supermassive black hole 40 million times more massive than our Sun. In fact, almost all galaxies have black holes at their centers, which are vital for their formation. Stars, they are basically a really big bunch of hydrogen atoms which are constantly bumping into one another and combining into heavier elements, mainly helium, but later also lithium, neon, oxygen and silicon. This process is called nuclear fusion, and the force that is exerted stops the star from collapsing in itself. However, after some billion years of nucleosynthesis, the star starts to produce iron. And that's when you know it's gonna be bad. Stars can't fuse elements heavier than iron, and because of the lack of force generated by nuclear fusion, gravity starts to take over. Small stars like our Sun will expand, become a red giant and probably eat Earth, and then collapse down to a white dwarf, the size of a planet. He's like, if I die, you come with me. However, stars that are more massive will start to shrink, increasing in density. Electrons will be forced to combine with protons to make neutrons, and the core will become a neutron star, all in some milliseconds. Because of some complicated stuff, the outer layer is ejected into space, with such an incredible energy, that it can outshine a whole galaxy. All that is left will be either a neutron star or a black hole. If the density of a neutron star is 400 quadrillion kilograms per cubic meter, then a black hole's is infinite, literally. More precisely, that's the density of the singularity, which is the center of the black hole. It also has zero volume, probably. All of the black stuff you see around is called the event horizon, and it isn't black, it's without color, like really. Because of the gravitational pull of the black hole, not even light can escape it, and therefore there is no light coming to our eyes from that region, and an absence of light is black. But hold on, you might say, how can light be influenced by gravity, if it is massless, and by definition, gravity affects only objects with mass? Well, that's what Newton thought. However, Einstein's theory of relativity says that gravity bends spacetime, and even light is affected by that curvature. Also, in theory, anything can become a black hole, if you compress it hard enough. That region is called the Schwarzschild radius. For example, you would have to compress the Earth to 9 millimeters or the Sun to 3 kilometers to get a black hole. Okay, back to black holes. Once stars turn into them, what then? Do they roam the universe hunting for different celestial bodies to eat? Do they live forever? That's what everyone thought until Stephen Hawking's discovery of Hawking radiation. Basically, in the vacuum of the universe, due to quantum effects, there are virtual particles constantly appearing and at the same instant annihilating each other, and therefore no energy or matter is created or destroyed. These particles have opposite energies and don't affect the outside world and during their small life, hence the name, virtual. But right at the edge of the black hole, these pair can appear, and one particle is pulled in the black hole, while the other one is ejected into space. This breaking of the particle-antiparticle bond results in the black hole losing energy, and thus mass. For a black hole the size of a sun, it would take a time bending 10 to the power 67 years to evaporate, while for bigger ones, 10 to the power 100 years. That's incredible. Just so that you know, the difference between these two is 10 times. Okay, enough with talking, let's jump inside one. But suppose we try and orbit it in a spaceship. As you can see at first, all around the black hole, you can see the light being distorted due to its gravity. All the light coming from the back of the black hole has its path distorted, and in a result, we can see even beyond the black hole, together with its both poles at the same time. As we advance, we are still in a stable orbit. You can observe everything around you having a bluish nuance. That happens because light trying to escape the black hole has a shortened wavelength corresponding to the blue part of the spectrum. As we slowly approach the event horizon, we start to get unstable. We have to use the thrusters of the rockets to keep in its orbit. At this point, we reach the photon sphere, where light itself orbits the black hole. Theoretically, we could see our own rocket by looking at the side, as the light reflected from the ship goes around the black hole and arrives back at us. As you might know, gravity also affects time. On Earth this is unnoticeable, but near such bodies with immense gravity as black holes, time would drastically slow down compared to someone watching you. They would see the spaceship venturing into the black hole. As it approached the event horizon, due to the time dilation, they would see you go slower and slower until you would freeze at the event horizon. Also, light coming from you would get extremely redshifted, and then disappear, as no light could get out. Meanwhile, from your perspective, as you get really close to the event horizon, everything would start to speed up outside the black hole. Your family, kids, grandkids, hundreds of generations will rise and fall in seconds for you. Billions of years will pass while you dive inside the black hole. After you pass the event horizon, this black border, there is no way out. Even if you would travel at light speed, you wouldn't be able to escape. It is literally impossible. If you were falling inside a black hole the size of our sun, the gravitational pull would be way more strong at your feet than your head, and therefore you would be stretched like a spaghetti, hence the name spaghettification. This would certainly kill you, but if the black hole is supermassive, the gravity won't be so powerful, so you might continue your journey for a little more. You would see the borders between the universe and the black hole change with places, and the universe becoming a sphere, brighter and brighter. This happens because all the incoming light would fall, forming a circle. It would become smaller and smaller, until all the incoming light would be concentrated into just one point. At this point. But if you were to go further, you would be left with everlasting darkness, no way of getting out. You could say that you wasted your time, all your time that you had, all the time that can exist. Congratulations. Now you are falling to the singularity, the center of the black hole at almost light speed, and as you are about to reach it, outside the black hole, the universe now is an empty space, with no stars in it, as they have extinguished long time ago. Only lifeless planets roaming around together with other black holes that are slowly evaporating. Oh, it's so romantic. In these last moments for both you and the universe, you will reach the singularity. And at this point, nobody knows what will happen, because thanks to these scumbag singularities, scientists couldn't merge the theory of relativity with the quantum theory. But hold on, your journey might yet not be over. If a star that is in process of becoming a black hole is rotating, correspondingly the black hole will be rotating for a little time. This type of rotating black hole is called a Kerr black hole. Because of its centrifugal force, it wouldn't be able to create a singularity. Instead, there would be a ring with no gravity, in which one might survive the tidal forces, and be transported to another place in the universe, or in time, or in another universe, or... This is all theoretical? Yes, there are some complex mathematics behind this Einstein-Rosen bridge, but nonetheless, this might be your best possibility for intergalactic travel. Thank you for your priceless attention, and congratulations, you are now on average smarter than someone who hasn't watched this video, so make sure to share it with your friends so that we can have a better society. Bye bye and see you in the next video.
Neutron stars are the densest things that are not black holes. In their cores, we might find the most dangerous substance in existence. Strange matter. A bizarre thing so extreme that it bends the rules of the universe and could infect and destroy everything it comes into contact with. Or it could teach us about how the universe began. Maybe both. To understand how extreme strange matter really is, we first need to get a few basics. What is a neutron star, and how does strange matter break the rules of the universe? To get all of this into one video, we'll grossly oversimplify a few things, but we'll provide you with further reading if you want more details. A neutron star is what remains after a very massive star explodes in a supernova. When this happens, the star's core collapses under its own gravity with such a strong inward force that it squeezes nuclei and particles together violently. Electrons are pushed into protons, so they merge and turn into neutrons. All the nothing inside of atoms is suddenly completely filled with particles that really don't want to be close to each other but have no choice. They desperately push back against gravity, against the collapse. If gravity wins, they will become a black hole. If they win, they become a neutron star. This makes neutron stars like giant atomic nuclei the size of a city, but holding the mass of our sun. And here, things get weird. The environment in the core of neutron stars is so extreme that the rules of nuclear physics change. And this could lead to a strange and extremely dangerous substance. But let's not get ahead of ourselves. We first need to know the rules before we learn how they can be broken. Protons and neutrons, the particles making up the nuclei of atoms, are made up of smaller particles called quarks. Quarks really don't want to be alone. They are what we call confined. You can try to separate them, but the harder you pull, the harder they try to pull themselves back together. If you use a lot of energy, they just use this energy to create new quarks. Quarks only exist together as the building blocks of other particles and have never been observed by themselves. They come in many types, but only two appear to make stable matter: the up and down quarks found in protons and neutrons. All other quarks seem to decay away quickly. But this may be different inside neutron stars. The forces operating in their cores are so extreme that they are actually similar to the universe shortly after the Big Bang. Neutron star cores are like fossils, which can let us peer back in time to the beginning of everything. So learning how quarks behave inside a neutron star is a way of understanding the very nature of the universe itself. One hypothesis is that inside a neutron star core, protons and neutrons deconfine. All the particles crammed shoulder to shoulder dissolve and melt into a sort of bath of quarks. Uncountable numbers of particles become one giant thing made purely from quarks. Quark matter. A star made from this is called a quark star, though from the outside it may not look any different than a regular neutron star. Now we can finally talk about the most dangerous substance. If the pressure inside a quark star is great enough, it may get stranger. Literally. In the cores of neutron stars, some of the quarks may be converted into strange quarks. Strange quarks have bizarre nuclear properties, and they are heavier and, for the lack of a better word, stronger. If they turn up, they could create strange matter. Strange matter might be the ideal state of matter. Perfectly dense, perfectly stable, indestructible. More stable than any other matter in the universe. So stable that it can exist outside neutron stars. If this is the case, we have a problem. It might be infectious. Every piece of matter it touches might be so impressed by its stability that it would immediately turn it into strange matter too. Protons and neutrons would dissolve and become part of the quark bath, which frees energy and creates more strange matter. The only way to get rid of it would be to throw it into a black hole. But then again, who cares? All of it is inside neutron stars. Except when neutron stars collide with other neutron stars, or black holes, they spew out tremendous amounts of their insides, some of which could include little droplets of strange matter called strangelets. Strangelets are as dense as the core of a neutron star. They could be really small, maybe even subatomic, but even the largest strangelets wouldn't be any bigger than a rocket. These strangelets would drift through the galaxy for millions or billions of years until they meet a star or planet by chance. If one were to strike Earth, it would immediately start converting it into strange matter. The more it converts, the more it would grow. Ultimately, all of the atoms making up Earth would be converted. Earth would become a hot clump of strange matter the size of an asteroid. If a strangelet strikes the sun, it would collapse into a strange star, eating through it like fire through a dry forest. This would not change the sun's mass much, but it would become way less bright, so Earth would freeze to death. And like a tiny virus, we'd have no way to see a strangelet coming. Worse still, some theories suggest strangelets are more than common, outnumbering all stars in the galaxy. These strangelets could have formed very early after the Big Bang, when it was as hot and dense as a neutron star core everywhere. They might be clumping around the gravity of galaxies as the universe expanded and evolved. Strangelets could even be so numerous and massive that they might actually be the dark matter we suspect holds galaxies together. But then again, maybe not. This is speculation, and the Earth and Sun and planets haven't been consumed in a wildfire of strangelets in the past few billion years, so the odds seem good that it won't happen anytime soon. Understanding these strange objects today may be the key to understanding the birth of our universe and why it grew to look the way it does now. When scientists first started playing with magnets and wires and thinking about electrons, they had no idea how technology would evolve in the next 100 years. The scientists thinking about the cause of neutron stars and strange matter today may be setting up humans for a future beyond our wildest imaginations. Or maybe not. Time will tell. So while you're waiting to see if the universe gets destroyed, you might still want to find out more about it. We've got you. Our friends from Brilliant can be your insight into a whole world of science, black holes and all. Brilliant is a website that helps you tackle science in a practical way, with interactive problem-solving courses and daily challenges in maths, logic and engineering. Each problem gives you all the tools you need to crack complex topics all by yourself. It's learning by doing, but with your brain instead of your hands. Use your curiosity to get to the bottom of puzzles and courses about things like classical mechanics, astronomy, gravitational physics, and much more. If you click the link in the description or visit brilliant.org/nutshell, you can sign up for free and learn more things than you can imagine. And there's an extra perk for Kurzgesagt viewers. The first 688 people to use the link get 20% off their annual membership, which lets you view all the daily problems in the archives and unlock every course. Brilliant helps you end your day a little smarter. You might get hooked on the experience.
I have a way out of this. Do you trust me? Of course! See you soon! I'll explain later. We jump on 3. 1, 2, 3!
Where are we? Not about to get eaten. Good enough for me.
It's more complicated than that. Twilight, you're okay. This is supposed to happen.
Oh, my things are horse things!
Around here we call them pony things. That wasn't quicksand back there. The sand was covering a portal to Equestria. I thought there was only one from school to Celestia's mirror, but who knows how many there are and where they might lead.
Sorry, I wasn't listening. Because we're ponies! You know, Twilight, since I kind of messed things up on the boat, maybe this could be your vacation. We're here, we're ponies. Let's have some fun! Pony style!
That's not a thing we say.
This would be a fantastic opportunity to study the physical laws of a novel dimension.
Shouldn't we be getting back?
It's just a little rain. I'm sure.
Wake up, theorist. I don't know if you're ready to see what I have to show you, but unfortunately the two of us have very little time. They're coming for you, and I don't know what they're going to do if they find you. I can help you, but only if you do exactly as I say. Watch this video and perhaps you will have a chance. Good luck. Hello, Internet! Welcome to Film Theory. I'm glad you decided to stick around because there is much we have to discuss. When it hit theaters in 1999, The Matrix was unlike anything anyone had ever seen before. Well, unless you keep up with any form of cyberpunk, had ever read a philosophy textbook, were a fan of Japanese anime or kung fu films, had ever watched Tron, you get the idea. But hey, that makes complete sense when you consider that the film's creators, writers, and directors, the Wachowskis, were absolutely massive fanatics of all of those things, and wanted to add to those genres with a film that incorporated elements from all of them. And the world they created, while accessible enough to be mimicked in hundreds of parodies long before poop emojis became a way to ironically say I love you, or less ironically, I have to poop, has long been debated and reinterpreted by the same over-analytical fan base the Wachowskis themselves hailed from. And you know that where there's over-analysis to be had, the theorists will follow. So I dug through the awesome first movie, the not-so-awesome CGI of the second, and the philosophical ramblings of the whole series, only to discover that we have been completely wrong the whole time. That the hero of humanity, named the One, he who was prophesized to bring about the downfall of the machines and reload the Matrix, is not Neo, despite his name being a clever anagram of one. No, put aside Keanu Reeves' highly emotive face. The One is in fact...
Me too.
Agent Smith, the cold-hearted, murderous hater of humanity and the bad guy trying to stop Neo, is in fact the hero who sets in motion the destruction of the Matrix and humanity's freedom. Let's see how far this rabbit hole goes. Now I'm gonna assume you need a bit of a refresher on what the heck this trilogy is about beyond white dreadlocks and Christ imagery. So let me do a real quick recap for you first. In the first movie, we meet Mr. Anderson. I can't do it. I can't do the voice. In the first movie, we meet Thomas Anderson, a hacker codenamed Neo, who is disillusioned with his job, his life, and reality itself, until mysterious messages lead him to Morpheus, who totally blows his mind when he tells him that the world as he knows it is a computer simulation, and humanity is enslaved by machines who use this digital reality, or the Matrix, to keep humanity submissive while they harvest their body heat for energy. Whoa. Turns out, Neo is the subject of a holy prophecy. He is the One, humanity's savior, who has the ability to transcend the laws of this digital reality in such an advanced way that he can do amazing, epic, not at all ripped off from Dragon Ball Z-esque things. All hail the coming of the One and the destruction of the Matrix, right? Well, as the architect explains in the second movie in a monologue that's gone down in history as one of the single most confusing things ever said by an actor in a major blockbuster ever, Neo's special status is all part of the machine's master plan. You see, another name for the One is the Prime Program. He's the result of an imperfect system. You know how when you divide numbers together, you sometimes get a remainder when they don't divide in perfectly? The One is basically all those remainders glommed together into a big number ball. And as long as he exists, the Matrix will remain imperfect and gradually descend into chaos until it crashes and destroys all of humanity, including its last stronghold, the sweaty dubstep-fueled rave cave of Zion. Long story short, humanity will be extinct. In order to prevent this, the One's code needs to enter the source, which allows the Matrix to reload and everything to become perfect and stable. Eventually, Neo goes to the source, jacks in, fights Agent Smith, an AI program tasked with keeping order in the system, loses, Or wins? And since Neo is plugged into the source over at Machine City, the anomaly goes bye-bye and the Matrix is able to finally be reloaded, bringing peace to the struggle between man and machine, with blind Jesus Neo being carried off into the light. The end, clear as mud. But what's easy to lose amidst all the black trench coats and bullet time effects are the details. For instance, let's look at the aforementioned prophecy. Quote, "When the Matrix was built, there was a man born inside that had the ability to change what he wanted, to remake the Matrix as he saw fit. It was this man who freed the first of us and taught us the truth. When he died, the Oracle prophesied his return and envisioned that his coming would hail the destruction of the Matrix and the war, bring freedom to our people." End quote. So if Neo is truly the one, he needs to have been born in the Matrix, is able to change it, and ultimately destroys it to set humans free. Let's start with the first criteria. Born inside the Matrix. No. Neo was not born inside of the Matrix. He was born in one of those gross harvest pods by the machines. He even has the extra electrical outlets on his body to prove it, which are so useful during the holiday season. To be fair, Neo was reborn inside the Matrix after being killed by Agent Smith at the end of the first film, but keep in mind that the Oracle's prophecy also specifies, quote, "when the Matrix was first built." And as we're told in the film, this is the 6th version of the Matrix.
The Matrix is older than you know. I prefer counting from the emergence of one integral anomaly to the emergence of the next, in which case this is the 6th version.
Mr. Anderson wasn't around way back then. You know who was, though? Agent Smith. Smith has been there since the beginning.
Did you know that the first Matrix was designed to be a perfect human world, where none suffered, where everyone would be happy? It was a disaster.
He speaks about it in a way that implies that he was there. But not only that, he goes so far as to call the Oracle Mom in the 3rd movie.
You would know, Mom.
So, despite him being just a computer program, the idea of birth still applies. But look at it a different way. At the end of the first Matrix, Neo jumps into Agent Smith, destroying him from within. But that moment fundamentally changes Smith. He's reborn in the 2nd movie as a rogue virus. As he explains to Neo,
"Because of you, I'm no longer an agent of this system. Because of you, I've changed. I'm unplugged. A new man."
Which just goes to show one other way that Smith was born inside of the Matrix. Okay, but let's move on. The second part of the prophecy says the One will be able to change the Matrix, to remake it as he sees fit. Although Neo shows some real promise at the end of the first movie with his jumping inside Smith fatality, that's pretty much the end of his endeavor to do any kind of next level hacking. Neo doesn't actually change anything throughout the sequels. Sure, he can do some kung fu moves and fly, but that's about it. When it comes to changing the fabric of the Matrix, the way it behaves, Smith shows far more power. I mean, check out how the Matrix looks by the end of the series when Smith is at the height of his power. It's unrecognizable. And very clearly, the one who made those changes was Smith. In his own words,
"You like what I've done with the place?"
But MatPat, you might be saying, don't you know that Smith is only special because Neo is special? When Neo jumped inside of him at the end of the first movie, he copied part of himself onto Smith. Interesting, theoretical theorist. So you're suggesting that Neo causes Smith's exceptional powers, but not so fast. The quality that determines if someone is truly the One is based on the ability to rebel against the machines. Like Morpheus says,
"Yet their strength and their speed are still based in a world that is built on rules."
That makes sense. Machines are just a series of zeros and ones, so of course they're bound by the rules of their programming. But wait, then how do you explain this scene? In the first Matrix, Smith takes out his earpiece while interrogating Morpheus and explains his desire to escape the Matrix.
"I must get out of here. I must get free."
And when the other agents walk in and see him without his earpiece in, they scold him. Smith is a program meant to ensure the security of the Matrix. That earpiece is his direct line with the system. And here it appears as though he's going rogue. Not only does the fact that Smith is able to go against the rules and take out his earpiece suggest his heightened ability to rebel, but everything he says in this scene is oddly human, talking about smelling and tasting humanity and being disgusted by them.
"It's the smell. I can taste your stink."
long before he takes on Neo, Smith is working against his programming. Smith, not Neo, is the anomaly in the system. And now for the final tenet of the prophecy, that he would bring destruction to the Matrix and bring freedom to the people and end the war. Okay, so although the saga ends with the Matrix still intact, it gets pretty banged up during the Smith-Neo final battle, and in reloading, one could say that it was destroyed. And look who says that he's actually going to destroy the Matrix. You guessed it. Smith. And the only reason that the war between man and machines ends is because Smith is so darn good at tearing up the fabric of the Matrix that the machines can't control him anymore. This precarious position Smith puts the machines in is what gives Neo the bargaining power to strike up a deal with Babyface over here that allows the humans who want to stay in the Matrix stay, and the EDM fans who want to leave and head to the concert in Zion go over that way and get all sweaty. Neo might be the one making the deal, but without Smith's uncontrollable power, the machines wouldn't need to end the war in the first place. But here's the detail that seals the deal. The Matrix will reload when the remainder code of the One enters the source. Smith openly says that he's avoiding returning to the source after merging with Neo in the first movie. In his own words, he's been compelled to resist the call.
Afterward, I knew the rules, I understood what I was supposed to do, but I didn't. I couldn't. I was compelled to stay, compelled to disobey.
But for that final battle, Neo uploads himself into the Matrix from Machine City. At the end of the battle, Smith, victorious, assimilates Neo into a final Smith clone. But then this breaks him up, and all the Smiths blow up for some unexplained reason. This always confused me. Why does Smith lose? It's really unclear, and it feels like a cheap ending for such an awesome villain until you consider what's happened. Smith infects Neo, who is jacked into the Matrix from Machine City, aka the location of the source. When Smith assimilates him, his code is getting jacked directly into that source. As the prophecy and the architect have said, the prime program in this instance has been reinserted. Look at how Neo's body and the wires he's connected to respond in the moment of his assimilation. In that moment, through Neo's assimilated body, Smith's anomalous code is reunited to the source, and the Matrix is finally able to reload. Let me make it clear. He is the One, but he's the unwitting one. He's the savior of humanity without even intending it, or wanting it for that matter. But that all leaves us with one final question, and it's a simple one. Why does everyone call Neo the One if he's not the one?
The One. The One.
The One. The One.
The One. The
One.
The One.
The One.
The One.
Sure, Morpheus and the Dirty Sweatshirt Gang may just be mistaken, but what about the Architect? Or the Oracle? These are two of the most powerful programs in the system, and they should probably know, right? Well, one of them does. In his rambling speech, the architect says it was the Oracle who created the One. Not only does this strengthen the whole mom argument with Agent Smith from earlier, but it also shows that she's the only person who truly knows the One's true nature, the One's true identity.
I'm not the One.
Sorry, kid.
And what does she do with that knowledge? She chooses to lie to everyone else about it. In the final lines of the franchise, the Architect and Oracle meet in the reloaded Matrix, with the Architect saying,
"You played a very dangerous game."
What's he talking about? What is this dangerous game? Well, it's a reference to the lie. She told everyone that the One was Neo when she knew it was Smith. Why would she do this? She says in these final moments that she wanted change. But what does that mean? Well, it was the only way that she could get peace. Had the machines known it was Smith all along, they would have assimilated him into the system earlier, and the war between humans and machines would have continued. But by misleading everyone into thinking it was Neo, it allowed Smith to threaten the fabric of the Matrix, to the point where the machines had to make a deal of peace with Neo. Creating an elaborate lie was the only way to truly change the system. The dangerous game was allowing a rogue program like Smith to get as powerful as he did. Boy, did she do a good job of covering up the truth, since it fooled all of us too, for over a decade. Agent Smith, that rainbow over there, it's for you, buddy. You truly are the One. But hey, that's just a theory. A film theory. And cut. Subscribe, dear viewer, and you will have your eyes open to the truth in the realms of TV and cinema. Plus, we have another Matrix episode coming down the pipeline, so you'll want to subscribe so you don't miss that one. But if you're ready to go further down the rabbit hole for more Matrixy goodness right now, then click here to check out my friends over at the Wisecrack channel, as they take a deeper look at the Matrix Reloaded, exploring all the details we've been overlooking for years that give us a sense of the movie's true hidden meaning. Or click here to just check out their channel. Chances are you watch Film Theory for thought-provoking movie and TV related videos, right? Well, these guys do just that, fusing education and entertainment into that sweet, sweet thing we call edutainment. I'm a huge fan of their stuff, and I think you will be too. So go ahead, click here, check it out. Now, if you'll excuse me, it is long past due that we talk about some Marvel. More on that next time. Mr. Nope, still can't do it. Damn.